Hi everyone and welcome to this episode of Keipert Labs. In today's video I'm going to show you how to construct redox half equations. Okay, so we're going to start by introducing the concepts around half equations, what we mean by those and how they connect to redox reactions, and then we're going to have a go at constructing some balanced half equations, so look at the processes and the steps that we'll follow, and we'll go through some examples of how to do it. Okay. So we've looked so far at the concepts of oxidation and reduction as processes involving the transfer of electrons from one substance to another, and that those two things are happening together. But it's often useful for us to consider both kind of processes in two parts. So we know that the process is happening together, but it can help us mentally to actually separate them into the two halves. One part representing the oxidation part, then that process and that reaction, the other part representing the reduction half or reaction. Okay, because then we can, even though they're happening simultaneously, you'll see when we start to get to galvanic cells that actually then by considering each half separately, it can help us to articulate what's going on more effectively. So each part or each section of this reaction is called a half equation. Okay, so it's only representing half of that particular reaction that's happened. Okay, recognizing that halves must come together to make a whole, but mentally, again, splitting it helps us. You'll see that as we go. Okay, and the idea is that in each equation, that's a half equation, there will be electrons present that show whether there was a loss or a gain of electrons in that particular process. Okay, so for example, the reaction of sodium metal burning in the presence of chlorine gas, or violently reacting with chlorine gas. We get this particular equation. So 2 lots of sodium metal reacting with 1 Cl2 molecule to form 2 lots of sodium chloride as a solid, because this is happening at in the presence of these reactants at a low temperature. Okay, so that it's not melted. So we want to consider the changes that are happening to the sodium to go from sodium metal to sodium ions, and the changes occurring in the chlorine to go from chlorine gas to chloride ions. Okay, so we can tease out those two halves. Okay, so we've got the sodium metal forming sodium ion. Now I know it's an ion, but then we're saying solid because remember that this is actually how it's forming, as strange as that might seem. And then we have our reduction of our chlorine gas gaining 2 electrons to form chloride. Okay, so we can see the electrons present in our two processes on opposite sides of the arrow. Keep that in mind, and that they're representing how those electrons are moving from the sodium to the chlorine to get this change to occur. Okay, so how do we actually go about constructing a half equation that's balanced and that's accurate? So we've identified which are kind of the main atoms that are changing in our process. And we make sure that we've balanced those atoms. Okay, so if there's, for example, iron, copper, manganese, chromium, whatever. Okay, so and if they're not oxygen or hydrogen, they're the things we balance first. Next, we balance the presence of oxygen atoms by adding water molecules to the other side of the equation. 1 water molecule for every 1 oxygen on the opposite side. And then we'll need to balance any hydrogen atoms by adding H+ ions to the other side. 2 of them for every water molecule that we have added to adjust for oxygen in step 2. And then the last kind of step that we're doing here is adding up the charges on each side. So what is the magnitude of the charge on the left-hand side and the right-hand side of the equation, and then balance that by adding electrons to the more positive side. And the difference between the charges being the number of electrons that must be included in there. Okay, I'll show you how that works in this example. Okay, so let's start with saying, all right, we've got the reaction where the permanganate ion is transforming into the manganese 2+ ion. Let's fill out an equation that describes that process. So step 1, we're checking that to balance the manganese atoms. So we've got 1 manganese on each side. So 1 to 1, so tick, that's correct. Okay, our next step, we're checking for our oxygen atoms by adding water molecules to the other side. Okay, so here we have 4 oxygens on the left and none on the right. So we need to add 4 water molecules onto the right-hand side to balance that out. Because remember, conservation of mass is still applying here. We're not gaining or losing any atoms in our process. They must be represented there somewhere. Okay, but in adding these 4 water molecules in, I've now contributed hydrogen atoms that weren't originally there. So now I check the hydrogens and I add H+ ions for every hydrogen atom that is present. So I add 8 H+ ions to the left-hand side to balance it out. And now what I need to do is I need to check what the charges, add up the positive and negative charges on the left side and then the right side and look at the difference between the two. Okay, so what I have here is that the permanganate ion has a charge of -1, and each of these hydrogen ions has a charge of +1. So I have 8 positive charges here and 1 negative. So overall, the left-hand side has a charge of +7. On the right-hand side, my manganese 2+ ion has a charge of +2. Then each of my water molecules is neutral, so it has a 0 charge. The fact that there's 4 of them doesn't change that fact. 4 lots of 0 is still 0. Hopefully early high school maths would have taught you that. So on the right-hand side, we now have a total charge of +2. So we've gone from +7 to +2 by electrons transferring. Okay, and so with the difference between the two sides is 5. So we've gone from 7 to 2, so a difference of 5. We add 5 electrons to the equation on the more positive side, which in this case is the left-hand side. So adding 5 electrons to finish off and tidy up our equation. So we can see that because the electrons are on the left-hand side, this is a gain, therefore a reduction process. So this is a reduction half equation. Now, we didn't know that from the outset, just looking at this. Now, if we had checked with our oxidation state, we could have identified that early before we actually did any balancing. But now, through the process of actually constructing this balanced equation, we've been able to identify that it's a reduction at the other end. Now, this kind of an equation is probably one of the more complicated ones you would encounter. Not the most, but right up there. The reality is that most of the ones that you're doing, you won't necessarily have to apply all of these steps. You'll probably only have to do the first and the last steps. So balancing out the atoms that are not oxygen or hydrogen, and then checking the charges and adding electrons in to adjust for that. Okay, but I wanted to walk you through a more complicated example so that you would know how to do it when you encounter them. Okay, so we introduced the concepts behind half equations and how they represent that half of the process that's happening, but mentally it helps us to separate out oxidation and reduction. We went through the processes of how we construct a balanced half equation and then went through an example walking you through those steps. Thanks very much for watching. Bye for now.